Okay, now we can also, just like we can put XY points into polar form, we can also put imaginary numbers into polar form. If we were to graph an imaginary number in the number a plus bi, we'd go a in the real direction and b in the imaginary direction and have this point a plus bi. We could also do a little right triangle and put a theta and an r in that and use theta and r to name the same point. So here's our usual cosine of theta and sine of theta relationships. A is r cosine theta, b would be r sine theta, just like we did with x and y. So we can write z equals a plus bi as z equals r cosine theta plus r sine theta I. If we do a little factoring out and rearranging of those, we get an abbreviation that's very handy to use. We say factor out the r, put the I in front of the sine theta, and look at these initials, RCIS, and we say that z is equal to r cis theta, where r is called the modulus, that's the distance from the origin to the point. If we were talking about vectors, that would be the magnitude of the vector. And sometimes imaginary numbers in polar form are used to work with vectors. Theta is the argument, which is inside of the function. We can also use our usual r and theta. We can convert from ab to r and theta using the Pythagorean theorem, making sure not to include I as part of the b, just the number a and the number b, but not the little unit I. And theta is inverse tangent of b over a. Adding pi, of course, for quadrant 2 and 3, and adding 2 pi in quadrant 4. And the reason we do that is because in polar form, it is considered good form to always have theta between 0 and 2 pi, a positive angle in the first rotation around the graph. We always want our r to be positive as well. So let's take a look at some problems. The worksheet that I gave you, that is the worksheet Complex Numbers in Polar Form. The first group of problems say convert the following complex numbers to polar form. And so here's a complex number. And remember, always draw a sketch. Always plot the point to make sure your answer is reasonable. So I'm going to go 3 in the negative real direction and 6 in the positive imaginary direction and plot the point -3 plus 6i. So what I'm looking for is this r and this theta. So I need theta to be a quadrant 2 angle, which means I'm going to be having to add pi to whatever I get. So r is going to be the square root of -3 squared, which is 9, 6 squared, which is 36, and that's the square root of 45, which turns out to be about 6.7. And theta is equal to inverse tangent of b over a. Oh, actually, what I want to say is inverse tangent of 6 over -3, which is -1.07. Now, that's not the angle I want, remember. That's the angle that is in quadrant 4. I need to add pi to that to get the angle I want. And that gives me theta is equal to let me check out my work, 2.03, which makes perfect sense because I know that 2 radians is in quadrant 2. The radius being 6 when this is 6 and this is -3, that makes perfect sense. So how do I write that? I write z is equal to the radius 6.7 cis and then the angle. Remember, cis means cosine 203 plus sine 2.3i. Okay, that's what that means. Okay, what about z equals 5? Putting that into polar form. Well, let's look what that means. This is 5 plus 0i. In other words, there's just a real part of the number, no imaginary part. So it's just plotted 5 in the direction of the real number. I don't even need to use any formulas for this. I can just look at that. What is r? Well, r is 5 because it's 5 units from the pole. What is the angle? The angle is 0. So z is equal to 5 cis 0. Now, in the next one, number 7, if you go down farther in the worksheet, this is where you're supposed to change then from polar to rectangular. So I have to remember that r cis theta means r cosine theta plus r sine theta times I. So here's my theta, here's my r. So z is equal to 10 cosine 5 pi over 4 plus 10 sine of 5 pi over 4i. And just remembering, let's draw. Where's 5 pi over 4? It's a 45-degree angle in quadrant 3. That tells me a couple things. That tells me it's a special angle. It tells me both A and B have to be negative, and it also tells me that A and B are going to be equal to each other since this is a 45-degree angle. Here's my 10, here's my 5 pi over 4. So let's just check that out on the calculator. If I do 10 cosine 5 pi over 4, don't like how long this thing takes me to type, but I'll get it done. Okay. Now, actually, I think I did a control enter. I just wanted to do enter and get the exact value. There we go, negative 5 square root of 2. Now if I go back to this up here and just change this to sine, so back this up, type in sin. Okay, notice sine and cosine do give us the same value, negative 5 square root of 2. I could also have used the decimal negative 7.07. Either one would be fine, but you might as well use the exact value when it's a special angle. So z is equal to negative 5 square root of 2 minus 5 square root of 2i, or you could say negative 7.07 minus 7.07i, both of which make perfect sense for the drawing. Now if you look at the other side of the worksheet, I'm going to clear this off for a second, you'll notice that there's some formulas, a formula for multiplying two complex numbers, for dividing two complex numbers, and later on for raising a complex number to a power. On the last one, raising a complex number to a power, the z1 and the z2 are still referring back to the same z1 and z2 that are used in 10 and 11. So that's where those r's and thetas will come from. Notice that when you multiply two imaginary numbers in polar form, you just multiply their moduli, their radiuses, and you add their angles. So we just do z1, z2 is equal to 10 times 5 cis pi over 6 plus 5 pi over 3. And that's 50 cis, and that's pi over 6 plus 10 pi over 6, if you put those into a common denominator, or 11 pi over 6. So the answer is z1, z2 is equal to 50 cis 11 pi over 6. Now when you're doing these kind of problems, when you get your angle, make sure it's between 0 and 2 pi. If it's too big, subtract 2 pi. If it's negative, add 2 pi. Sometimes you'll have to do that more than once to get the angle back into this correct, the preferred form, the preferred domain. So I'm not going to do any more of these because I think these are fairly self-explanatory. There is a key on the bottom, and I will also post the complete worked out key to this worksheet as well. Hopefully this was helpful.